Aloha everybody, my name is Maria Jose Juan Jorda. It is my pleasure to be able to participate in this session of the challenges and successes of marine species conservation. Today, my colleagues Andy Cooper, Hilario Morua, Aritz Arrizabalaga, Nicolas Dalby, and I would like to share with you some ongoing research using the IUCN Red List Index to track oceanic biodiversity change in the high seas. Why are we estimating the Red List Index for highly migratory fish species? As you are all aware, the state of marine biodiversity in the high seas is poorly known. There is an urgent need to develop ecological state indicators to measure marine biodiversity change to support international treaties on biodiversity protection and fisheries governance, especially for the high seas. Therefore, we're using the IUCN Red List Index to develop an ecological indicator to track oceanic biodiversity change in the high seas, and we're using oceanic tuna, sharks, and billfishes as sentinels of ocean health. Oceanic fish species provide a unique opportunity for the development of ecological indicators. Why? They sustain important commercial fishes worldwide and have a great wealth of data and knowledge. Many of these species have been assessed by regional fisheries management organizations, and we know how their populations have fluctuated over time, which is key to calculate the Red List Index. As a case study, we're presenting here the Red List Index for the Pacific Ocean. Before I can show you the Pacific Red List Index for tuna, sharks, and billfishes, it is important you know the main building blocks of this analysis. First, we assess the oceanic biodiversity number of species of tuna, sharks, and billfishes in the Pacific Ocean, and found 31 species, 6 species of tunas, 19 species of sharks, and 6 species of billfishes. However, of these species, 40% of them have been evaluated with fisheries stock assessments by the 3 regional fisheries management organizations in charge of managing these species in the Pacific Ocean. Fisheries stock assessments provide us with key information such as estimates of abundance and biomass over time and generation length, which is critical information to estimate the IUCN threat status of a species and therefore the Red List Index. We also learned that 60% of the species, mostly sharks and billfishes, as you can see here in this figure, have never been assessed with fisheries stock assessment. Therefore, for these species, we lack information about their exploitation status and biomass trajectories over time, which will not be included in the Red List Index. On the contrary, all the tunas have been assessed and their exploitation status is well known. Third, we calculated the IUCN threat status for all the assessed species of tunas, shark, and billfishes, and we did this retrospectively from 2014 all the way to 1965. And here I'm showing an example, the estimation of threat status of one stock, the yellowfin tuna in the West Pacific, and how we estimated the threat status over time, starting with the last year of data in 2014 all the way to 1965, as you can see here in the following next slides. So from 2014 all the way from 1965. As you can see at the bottom of the slide in the bar plot, we are recording the threat status at each time step and the probability of being in each IUCN threat status category. At the beginning of this time series, we find 100% probability of being categorized as vulnerable, see the orange bar. Then we see a decrease in the probability of being categorized as vulnerable and an increase in the probability of being categorized as least concern, see the mixed colors bar with some orange and some green in them. Then towards the end of the time series, we find 100% probability of being categorized as least concern, see all the bars are all green. How are we estimating probabilities of being in each threat status category over time? We're using a Bayesian framework to estimate population changes within 3 generation lengths for applying the IUCN criteria. Here we're showing two more examples, the threat status over time for southern bluefin tuna and yellowfin tuna in the Indian Ocean. And the color bars are showing the probability of being in each of the threat status categories for each year and each species. As you can see, the southern bluefin tuna from the 40s to the 60s, the population declines within 3 generation lengths. The population declines within 3 generation lengths were less than 50%. Therefore, the species was listed as least concern with 100% probability. Then the population continued to decline progressively during the next 4 decades, registering declines of more than 50, then 70, then more than 90% declines. At the end, the species was listed as critically endangered with 100% probability since the middle of the 90s. In the case of yellowfin tuna, this species started to be exploited a bit later. Declines were below 50% until the mid-90s, and in 2015, we estimated a 60% probability of being classified as vulnerable and a 40% probability of being classified as endangered. So by estimating probabilities, we allow the uncertainty in individual time series to be transparently propagated and changes in the direction in the threat categories to be detected. Here, we're showing the IUCN threat status over time for all the species included in the Red List Index, a total of 12 species, a total of 19 stocks. And the color bars are showing the probability of being in each of the threat status categories for each year and each species. As you may know, the calculation of a Red List Index requires that the same set and number of species is included in all the time steps. As you can see here, the first year at which the threat status is known differs among species because the starting year of biomass varies greatly among the stocks, and also the generation length also varies greatly among species. Therefore, in order to estimate the Red List Index and include all the set of species, we assume a Red List threat status category of least concern for those species and years with a known threat status category. This assumption is conservative because it is assuming fish mortality started the first year when the data is available, and this might not be the case for the majority of the population. Therefore, we consider our Red List Index for the Pacific Ocean to be conservative. Finally, using the yearly threat status for this group of species, we calculated the Pacific Red List Index for oceanic tuna, sharks, and billfishes, as you can see in this figure. The Red List Index tracks the trends in the overall threat status and the overall threat status or overall extinction risk for this group of species from 1965 to the year 2014. Therefore, this index provides a key measure of the rate of biodiversity loss and whether this is being reduced or is intensified. So in this case, the Pacific Red List Index for highly migratory fish species shows an initial decline until the mid-1980s, followed by a slight recovery and subsequent stabilization. And at the end, we observe a downturn resulting from the inclusion of the critically endangered oceanic white-tip shark. The Bayesian framework allows us to calculate credible intervals around the Red List Index point average, and this is very important because it allows us to assess the robustness of the overall trend. To our knowledge, this is the first time the Red List Index has been estimated for fish species, and we think it could be used as an ecological indicator to measure the rate of biodiversity change in pelagic ecosystems. In summary, we can use this Red List Index as an ecological indicator to track oceanic biodiversity change in the Pacific Ocean. We're also carrying out a simulation analysis to evaluate the performance of the index and the effect of the sample size over time to produce robust trends in the Red List Index. Remember, not all the oceanic fish species in the Pacific Ocean were included in the Red List Index due to the lack of data about their trajectories. We're also developing a global Red List Index including oceanic fish species from the Pacific, Indian, and Atlantic Oceans. Thank you very much. If you have any questions or suggestions, please contact me. Aloha!